So here is a solution for problem C, mission improbable. It can be easily noticed that each unique number that is observed from the side cameras can be treated independently. So for example, let's consider all columns and all rows where the maximum is equal to number 5. Those columns and rows will intersect at some subset of cells. And if there would be no third camera which looks from the top, then what we would do, we could greedily allocate some 5s so that both rows here and all 3 columns are covered by at least one 5, and the rest we would assign 0s. However, this is not possible providing there is a second camera, third camera, and therefore what we have to do, we have to put 0s where we should place 0s, and then we choose where to place 5 and where to place 1. It's quite logical that we need to place as few 5s as possible. Which means that we want to maximize number of 5s that cover both some column and some row. And this already looks like a bipartite matching problem. And to be precise, we take all cells that are not 0s, then we make a graph where columns and rows are vertices, and those cells correspond to edges. And then we can find maximal bipartite matching in that graph. And in the edges where that are selected in that matching, the corresponding cells should have a 5. And then we can greedily assign 5 also to the columns or rows that are not covered. And that is guaranteed to be least number of 5s we can put, because this is also equivalent to smallest vertex covering set. And by repeating the same procedure for all numbers, we cover everything with some values, except for maybe some cells that are not that are overlapping, not the same values on the right side and the bottom side, and there we can simply put 1. And this is the solution.